So now that you know how the A-star algorithm works, I want to go a bit into the theory and give you some properties of the algorithm. These all rely on the fact that the heuristic used is admissible, and we will talk about that first. A heuristic is called admissible if it never overestimates the distance from a node to the nearest goal node. So what this means is that the value of the function h of n must always be less or equal than the actual distance to the nearest goal node. The equality is actually quite important. For example, the heuristic value of a goal node is equal to 0, and therefore it's equal to the actual distance to the goal node. So any heuristic must have that property. In other words, there's usually at least one node for which the equality holds, namely the goal node. Unfortunately, this is often the only node for which this holds. Otherwise, we would have a perfect heuristic, and that is too good to be true. Admissible heuristics usually think the nearest goal node is closer than it actually is. They tend to underestimate the distance to the goal. An example of an admissible heuristic is one we have seen for the Turing-Romania problem, namely the straight line distance. The shortest distance between 2 points on a map is usually the straight line, hence the straight line distance heuristic must underestimate the actual distance along a road. Thus, it is an admissible heuristic. For A-star search, here's what that means. We set that the evaluation function f of n represents the cost of the shortest path through node n to a goal node. So if the heuristic never overestimates the distance from n to the nearest goal node, then the evaluation function used by A-star never overestimates the true cost of a solution through the node n. This brings me to the most important property of A-star, namely that it is optimal. We can prove the following theorem. A-star, using tree search, is optimal if the heuristic h is admissible. Just as a reminder, optimal here means that the algorithm is guaranteed to find the shortest path from the initial state to a goal node. And this theorem tells us that if our heuristic is admissible, then A-star will return with an optimal path. That is, of course, a very useful property for a search algorithm to have. By the way, a similar theorem can be shown for A-star using graph search, but I won't go into this here now. Another property of A-star is that it is complete, which means that if there is a solution, A-star can find this solution. This can be shown using something called contours. And since this is quite an interesting concept, I want to introduce this here. So contours are sets of states that can be reached within a certain cost. This is a bit like a topographic map that you've all seen, I hope. In a topographic map, you see lines indicating points of equal altitude. Here, the contour is a line indicating nodes of equal f value, and all the nodes within the contour belong to the set. A prerequisite for being able to draw contours is that the f values along a path are non-decreasing. So, what this means is that as we move away from the initial state, the f values are usually increasing. Now, the way A-star works fundamentally is that it starts from the initial state and then adds nodes according to these contours. It always starts with a smaller set and then increases the f value as it goes along. But it will always explore nodes with lower f values before it moves to a higher plateau, so to speak. If our heuristic function always had the value 0, what A-star would do is essentially draw circles around the initial state. If the heuristic always had the value 0, this would of course be uninformed search, and in fact this algorithm has a name. It's called uniform cost search, or Dijkstra's algorithm. But with a heuristic that provides some information, what happens is that the contours become ellipses that are drawn towards a goal state. So they try to get closer to a goal state. And the more accurate our heuristic is, the more these ellipses stretch towards a goal. The completeness of A-star simply follows from this, because as it explores more and more nodes, the contours are growing and growing, and eventually this must include a goal node. This is true because each contour can only contain a finite number of states, and once these are all explored, A star will go to the next higher altitude and explore a bigger contour. And here is what this looks like visually for our touring in Romania example. We start off in Arad, and the F value there was 366, so that's the smallest contour from which we start that contains a node at all. Then A star will continue to grow this contour. Initially it's a small set, but then we have a slightly bigger set. That, for example, has the value 400, and as you can see, this node here is almost on the edge, and if you go back to the tree, you will see its F value was above 400, so it must be outside the set, and so on. So A star continues to grow this contour until it includes the Bucharest node. In this example, you can see nicely how the ellipses it draws stretch towards the goal node. But you can also see it the other way around. What this means is that A star must explore all those nodes that are within a contour that has a value just less than the cost of the optimal path. A star needs to include all those nodes that are within this contour that almost leads to the goal node. And often that is still quite a large number. So in this example, you see that most of the contours contain different nodes. But think about the 8 puzzle for a second and what that looks like there. In the 8 puzzle, the maximum goal distance you have is 31 steps, yet you have just over 180,000 nodes. So there must be many nodes that have the same F value. Here is another property of A star, namely, A star is optimally efficient. What this means is that no other optimal algorithm is guaranteed to expand fewer nodes than A star. This is of course true for a given specific heuristic function. What this gives us is that any other algorithm that guarantees us an optimal solution must expand at least as many nodes as A star for a given heuristic function. Of course, there can still be a more efficient way of finding a solution to a given problem, namely if we have a different, more efficient heuristic. But for a fixed heuristic, A star is optimally efficient. Notice that efficiency here is counted in the number of nodes that are expanded, but of course that's not the only thing that makes an algorithm efficient. For example, computing the heuristic function has a computational cost, but it does not count towards the number of nodes that we expand. So A star is only optimally efficient with respect to the number of nodes it expands. To be more specific, it's not only the number of nodes that any other algorithm must expand, it is exactly those nodes. Suppose there is another algorithm that is optimal, which means it returns an optimal path, but it does not expand one of the nodes that is expanded by A star. What does this mean? A star expands all those nodes with an F value that is less than C star, where C star is the value of the optimal path. So if another algorithm did not expand one of these nodes, that means in the search space of the algorithm, there is an unexplored node that has an F value of less than C star. So that means the most promising path through that node that the algorithm ignores looks better than the optimal path. So if we don't explore that path, we can never find out that it actually turns out to be something worse in the end. So in the end, A star expands a minimal number of nodes that still guarantee an optimal solution.